Today we'll take a look at numerical or approximate integration. We'll review how to use traditional Riemann sums to approximate a definite integral using the midpoint rule. And we'll look at two new techniques using the trapezoid rule and using Simpson's rule. So why do we use approximation? We hinted at this last time, but sometimes we can't easily or at all evaluate an integral directly. Things like this one, integral from 0 to 1 of e to the x squared dx, or the integral of -1 to 1 of the square root of 1 plus x cubed. These look pretty simple, but pretty hard to deal with, or maybe not possible to deal with using elementary functions. Another example, sometimes we describe a function with a collection of data points, maybe readings from instruments or so on, and we don't have an explicit function that we can write to represent that data. We can still use those data points to analyze things that we could use integrals to analyze, like area under a curve. We could also, though, another approach is to use a regression in order to fit a function. That's, again, a different approach than what we're looking at here. But that's another way to estimate. If we approximate a set of data using, say, a polynomial function, then that's another way to approximate an integral. But here we're actually going to look at some other techniques using simply a set of data points without any regression involved. This should look somewhat familiar to you. You must have discussed these in Calc 1 at least a little bit. Riemann sums are a good way to set up a series of rectangles, a sum of a few different rectangles, or maybe many rectangles, in order to compute an approximate area under a curve. You probably saw that as the delta x gets small, as you create more and more rectangles, you're getting a better and better approximation of that sum, of the integral. We will review briefly this midpoint formula, the one on the right, a little bit, but only to relate it to the first new rule that we'll look at, which is the trapezoid rule. So, as you might expect, the trapezoid rule looks very similar to a Riemann sum, except instead of using a series of rectangles, we're using a series of trapezoids. Visually, taking a look at this, it looks kind of nice. You can imagine that it might give us a better approximation for small values of n, for smaller numbers of trapezoids. And that's one reason that it was developed. Remember, though, that since we're using area of rectangles for Riemann sums and area of trapezoids for the trapezoid rule, we need to apply a different formula when we set up our sum or our integral. So our sum is going to look like this, right? The area of a trapezoid, we say 1/2 times the sum of the bases b1 plus b2 times the height. But notice that these trapezoids are all going to be tilted on their sides, right? So b1 and b2 are essentially the two vertical side lengths here. Those will be function values that we'll be using, either by plugging in numbers into a function or by reading from a table. And then the height of the trapezoid actually is represented by your delta x value. So that's kind of represented here, right? We plug in x into a function, or we read output from a table. For our function values, we use delta x as the height. And then, again, we can iterate this as many times as we need to. Kind of matching the picture here, we'd start by using x sub 0 and x sub 1 for our first area. That would be the area of this first trapezoid. Then we could compute the area of the second one using the function value of the first and second x1 and x2 values added together, and so on, until we get to the end, right? The last one, x sub n, in this case it would be x sub 4, would involve the function value of the x previous plus the function value of that one itself. So maybe you notice a pattern here. Some of these function values are being reused. In fact, all of the ones except for the first and last, we will actually see twice in our when we're adding a bunch of these areas together in our sum. And that's kind of summarized here, right? We don't use the first and the last one twice. We only use those once. And you can picture this as drawing the trapezoids, right? If we were to sketch out the border of all these trapezoids, we'll only use the left side once and the right side once. But if we were to sketch those inner trapezoids, we're going to include all those inner ones again. And so that's reflected in our formula, right? What we can do is we can actually factor out 1/2 from the sum of all those different function values and then combine like terms. And we'll end up with f of x0 and f of xn only occurring once. But the other f of x values, f of x1, f of x2, all the ones in the middle, occurring twice. Having factored out the 1/2, we end up with 1/2 times the sum of those following that pattern. 1, and then a bunch of 2's, and then at the end a 1, and then our delta x at the end. This is the formula that we'll use for the trapezoid rule. You're going to be able to apply this formula to be able to decide what delta x is if it's not given to you. That would be your final x value minus your initial value divided by the number of trapezoids being used. You may, depending on the problem, need to identify what those intermediate x amounts are, but a lot of times those will be given to you. And then the really only reason you need those is to evaluate the f of x's, the function values at each of those places. Let's take a look at an example. We'll review midpoint sums briefly, and then we'll look at the same example using a trapezoid rule in addition. So think about back to how you might set up midpoint Riemann sums for this one. We're going from 1 to 2. We want to use 5 rectangles. We're integrating the function 1 over x. So notice the midpoints of those rectangles are where we're going to read the function heights. And those would correspond to x values of 1.1, 1.3, and so on. And so our goal then would be to plug those series of x values in to the function to get the outputs, the heights at each of those places. And then add those together. Again, we're just multiplying base times height here. We're multiplying a delta x, a base length, times a height, a function value, and summing a bunch of those together in order to get an area approximation. And so we're essentially multiplying by that delta x of 1/5 times the sum of all those function heights, the sum of all those rectangle heights, 1 over 1.1. Again, we're just plugging those x's into our equation, y equals 1 over x. And when we do that, we calculate an amount that's about 0.692, roughly. We'll compare that to our result that we get using the trapezoid rule. So same problem using the trapezoid rule. We want to estimate this integral. Once again, we can calculate the values to use here. Remember, we're thinking about the bases, right? So the base, and sorry, these are still rectangles that are drawn here, but our first trapezoid would look something like this one. Our first base occurs when x equals 1, and the second one x equals 1.2, and so on. Following the pattern there, if we're setting up the sum using 5 trapezoids, our delta x is the same. I wrote it as a decimal here for some reason, but our delta x is the same, 1/5. But we have the 1/2 that's written in front there that comes from the 1/2 of the area formula for a trapezoid. And then inside we've got that pattern of function values. We have 1 of the first function value. We have 2 of all the middle function values from those intermediary x's. And then we only have 1 of the last function value, right? So we plug in 1 and use that once. We plug in 2 and use that once as well. 1 over 1 and 1 over 2. But then we plug in those other 4 middle values for the bases and use those twice each. Again, following that pattern 1, 2, 2, 2, 2, 1. In order to compute that, we just add up all those function values, then multiply by 1/2 and by 0.2. We get a very close amount, 0.695635. This is not the best example, maybe it's a good example, because we can solve this integral directly really quickly, right? Remember, the integral of 1 over x just becomes the natural log of x. And if we evaluate that at 2 and 1, remember the log of 1 is just 0. So our exact value should be the natural log of 2 for this one. You can compute that and verify that this decimal is very close to the natural log of 2. If we had used more rectangles or more trapezoids, then obviously that would be a better approximation. One other rule that we'll take a look at is Simpson's rule. This is a little more complicated, but there's a very similar formula that we'll resort to. But we'll talk for a minute about where it comes from briefly. Instead of using rectangles or trapezoids, we use a series of parabolas, which that gets a little messier too, because we're trying to fit this curve to a bunch of different parabolas, and we're estimating those, and then we're using the sum of those to make an area. So we're not going to get bogged down in the proof. Don't worry too much about it. You can look it up if you're interested. But it boils down to a very similar formula as we would use, except with different coefficients. A key thing here is, though, that we need to assume that n is even. And you'll see why. What we need to do is essentially we need to modify a couple things from our trapezoid rule in this formula. Again, it's an interesting proof, but we don't have time to delve into that too much. But the idea is making a comparison to the trapezoid rule. We replace 1/2 with 1/3. And that comes kind of to do with the area under these parabolas. But we also replace some of these coefficients. There's still a 1 for the first coefficient and 1 for the last coefficient as well. There's still a delta x at the end. But what we're doing here in the middle is we're changing our pattern. Instead of a series of all 2's as coefficients, we're going to go from 1 to a 4 down to a 2, and then we'll alternate 4, 2, 4, 2, 4, 2, and then we will end up with a 4 and finally a 1 at the end. Again, don't worry too much about why that looks as it does. That's the pattern that we'll need to use. You can look into it if you'd like. But essentially that's doing the same sort of thing. That's computing area under a bunch of parabolas and averaging them out, essentially. So let's try it once. If we let n equal 10, that means we're going to approximate the same thing. Let's do the same exact integral as before using Simpson's rule. That means we're going to set up a delta x of 1/10 or 0.1. That comes from 2 minus 1 over 10. We use a 1/3 because of the Simpson's rule formula, including that instead of a 1/2. And then we're matching our coefficients 1, 4, 2, alternating 4's and 2's until we get to the end, which will be a 1. Since we assume n is even, it will always keep that same pattern of 1, 4, and then ending at 4, 1. Using the correct x values, we start at f of 1. And then since delta x is 0.1, the next function value we use is 1.1. We add that delta x in there. And we keep adding delta x to see what function values we're going to need. And so don't panic, right? We have the 0.1, that was the delta x that we wrote at the right side. I brought it to the left, divided it by 3. And then we've got our function values. 1 over 1 plus 4, that comes from this constant, over 1.1. That's the function's value at 1.1, plugging it into 1 over x. And do the same thing for each of those other intermediate values. Find the sum of all of those, multiply by 0.1 over 3, and we'll get, as we expect, a number that's very close to what we expected before, the natural log of 2.